Okay, welcome everyone. Thanks for joining. Today, or this evening, we are going to cover random forest and boosting. So thanks for joining. I hope you enjoyed the session on decision trees and you followed the content because this is an extension of that. So it is important that you understand decision trees for this section. Not in too detail, but just at a high level, how a decision tree works and how it makes its decisions, right? And you're going to use that, which feeds into random forests and into boosting, right? So that's what tonight is going to cover. So we've got a lot to cover tonight. So I'm just going to get straight to it. I'm just going to share my screen. Give me a second. All right, if you can't see my screen, let me know. I'm sharing what you'd see here is it's a SMAA random forest. Okay, but let me know otherwise. Okay, so it's going to come back to you here. Give me a second. All right, great. Let's kick it off. Now, let's start off with random forests. We're going to do random forests first, and then we're going to do boosting. Now, these algorithms, that is random forests and boosting, they fall under a family of models called ensemble models. Now, ensemble models just basically means taking many weak learners or weak models, combining them and making a model that is strong, that's collectively made of weak learners. So how did this idea start? Well, a while back, right, there was an experiment done, and what the experiment was that a statistician observed that 800 people who guessed the weight of an ox actually did a better job than one individual who would be an expert. But how you would use those 800 people's guess or prediction is you could average them out. So as long as they had some idea, they didn't have to be an expert. You know, they had some idea how to guess the weight of an ox or what a typical weight of an ox is. If you collectively looked at them, so in other words, those 800 people who you can consider weak learners, if you combine them and took their prediction collectively as an average, you could do better than taking the guess of one single expert. And that's kind of the underlying principle of an ensemble model. So random forest works like that. Okay, what it does is it takes many decision trees, like what you covered last week, it combines them together and it looks at all their predictions collectively, and then it can, if you're trying to predict a label or a class, as in classification, then you would look at the majority vote. So if 2 out of 3 trees voted this person would default on their loan, then that would be the prediction because 2 out of the 3 voted that, the majority. All right, so that's the underlying principle about it. And let's go about explaining how it actually does it. Now, in order to understand how it does it, it's very important that you understand something called bootstrapping. And all bootstrapping is, it's just sampling with replacement. Some of you may have heard of that. Some of you may have not. It doesn't matter. I'll cover that now. All right, so let's say you had some data set, right? And in this data set, you had, you could think of it maybe 10 people in it, all right? And they were customers, all right, for some product. Now, in this graph, so let me just disable something here on the, oh, all right, I think we're good to go. If you look at this first block is our training data, okay? So we have 10 observations, and these 10 observations of these 10 people are represented by different colors, different colored circles in that rectangle. All right, so those are the 10 people. Now they all have different colors because they're people, they're unique. All right. So what we do is we would sample with replacement. So if you look at this first learner here, and I'm going to draw your attention to this first learner. What we do is we draw a circle, as in pick a circle from this training data here. From the block above, we pick a circle. And in this case, we end up picking this light brown first, yeah, which is this person here. And then what we do is we actually allow this person to go back into the pool and we draw again. And when we draw again, we just so happen to pick this person twice. So you can pick this person twice, even though you're obviously not going to have two people, you're not going to have a clone. But from a data perspective, we can have this person captured twice in our data set. That's basically sampling with replacement, or in other words, that is bootstrapping. Now, random forests and all bagging models, which I'll explain in a second what bagging is about, they make use of this sampling technique, right? We allow each of the learners or the trees that make up the random forest to sample with replacement from the original data set. So that's why you can see for learner one, you can see there's colored circles that are repeated because it's allowed to sample with replacement. Just like learner two, if you look at learner two, you can see it sampled the purple dot 3 times, right? Sample the purple dot 3 times because it can sample with replacement. So you get the idea. So we'll keep it simple with just 3 learners. Okay, but just keep in mind in practice, random forests often use a lot more learners, right? To actually get the most benefit out of it. Some problems use at least 100 trees. But if you get the idea for just 3 of them, the idea is exactly the same when you use more learners. Okay, so that's the takeaway from this session. Just understand the methodology behind it. All right, so each learner is allowed to sample with replacement, so they can't have duplicates in them. All right, so tree 1 or learner 1 has that sample, learner 2 has that sample, learner 3 has that sample. And what you can take away from this is that because of that sampling with replacement, the observations in each of these learners don't necessarily have to be the same as what you have in your original data set. And it's a strength of the model to have that. You don't want that. The reason why you don't want every tree to have the same data is because you're likely going to get the same result for each learner. So it removes that benefit. What you want is each learner to have a different set of samples based on the original data, but you don't want them to be the same. You want them to be trained differently. You want learner 1 to focus a lot more on maybe these brown points than learner 3 maybe, for instance. All right, so the more points they have of that, then that means learner 2 gets to focus a lot more on the purple points than the other learners. So each of them have their own strengths, and you combine the strengths, and it makes one strong model in the end. All right, so let's move on to the next slide. But just shout if you have any questions. So now I'm going to show you with actual data. All right. So we've done bootstrapping, which is sampling with replacement, and now we're going to talk about bagging. Now, bagging, all it is it's just training a model on that sample. So in other words, if I just go back one slide, here we've picked our samples for learner 3. But as soon as we fit this model, so this learner or this tree 3, as soon as we fit it onto this data or train it on this data, then it's called bagging. That's essentially what bagging is. It's training different models on a different set of samples, right? And then you're going to combine them. So that's what it is. And the benefit, as I said earlier, is that, you know, if one tree is weak, then another tree can compensate for that, all right? Because you're adding the combined predictions of all these different trees. And I'm sure you're very familiar with the high variance, low bias for overfitting. Judging from your assignments, you know, it seems like you understand that concept. All right, so decision trees are known for having a high variance. So in other words, they're known to overfit. They do have a problem with that, especially as you increase the depth. Random forests can solve that problem by combining all those trees. So that's the benefit of doing this. Sorry. 1 second. All right. Now each tree or weak learner, right? I'll use those terms interchangeably, right? That is a question. Okay. All right. Okay. So random forest, right? Each tree, there's a difference now with random forest from all different other bagging models. Now, other bagging models would use all the same variables that you have in your original data set. So in other words, let's look at this data set here to kind of give you an idea of what I'm talking about. In this data set, you have 6 variables, right? I'll show you the 6 variables. Variable number 1 is age of the client. Variable number 2 is the age of the vehicle. The mileage of the vehicle is the 3rd variable. The 4th variable is the number of claims this client made for insurance. Here's the 5th variable, which is, do they live in an urban area? Yes or no? And then the 6th variable is, do they have any prior violations? Now, what you're trying to predict here, this target variable in the last column, is you're trying to predict whether this client will make an insurance claim. All right, so it's a classification problem. So you have 10 clients. Okay, that's where your client ID goes all the way up to 10. You have 10 clients, and essentially you're trying to use these 6 variables to predict whether these clients are going to make an insurance claim. All right, so those are the 6 variables. Now that's your original data set. So what you do with tree 1 is you don't give it all the features. You just give it a subset of features. In other words, you don't give it all, you just give it maybe 2, age and annual mileage. It doesn't get all 6. All right, that's what we call subsetting. All right, you're taking a smaller set from the bigger set. Right, you have 6 features originally, but you're only taking 2. Now, how do you know how many features to give these trees? Now, random forest has a built-in calculation that happens in the background. Right, when you implement this model, what it does is it looks at the number of features you have. In our case, we have 6 features, so our P is equal to 6. Right, we have 6 features. And when you're dealing with a classification problem, what it does is it works out this value here, square root of P. So in other words, if you take the square root of P, you will get something like 2.4, so roughly 2. So that tells the algorithm to give all these trees of the weak learners, give them about 2 features each. And that's why you're getting 2 features each for these trees. And so that's why tree 2 gets vehicle age and urban area, and then tree 3 gets prior traffic violations as well as no claims. Just keep in mind that trees or these weak learners can have the same features. There's nothing stopping it from having the same features. So tree 3 could also have urban area as well. All right. So just keep that in mind. There's nothing, especially when you're working with 100 trees, you're definitely going to have some trees sharing common features, but they won't get all the features from the original data set. So random forest does this. You get, let's say we just had 3 trees that make up our random forest. So I'm just going to clear something up here. Okay, so you got tree 1 that has those features. You got tree 2 that has those features, etc. So what you do is you train this tree, you fit it. Okay, you train it or fit it. Right, you do the same thing for tree 2. You train it and fit it on this data with those features. And you do the same thing for tree 3. You train it or you fit it to the data. So now each of these trees can make predictions over their client will default. All right. But now let's see how we use that to make predictions. All right. How do we combine these 3 trees? So we trained them, we fitted them to this data that you see here. And now we want to make use of it by applying it to someone new that comes to the door, and we want to make a prediction whether they're going to make an insurance claim or not. I'm just going to come to the chat and see if there are any questions. So far, so good. All right. Okay, so let's go to the next page, and I'll show you how we use this to make a prediction. All right. Now, we use something called majority vote. All right. So remember those 3 trees that I showed you in the previous slide. So here's the first tree, tree 1, tree 2, and tree 3. We have these new clients coming through the door. All right. And we are going to make predictions for each of them. So tree 1 will make a prediction of client 1, all right? And it predicts that this client is going to make an insurance claim. If you look here, it's got a value of 1. Then tree 2, it, however, predicts that this client is not going to make a prediction because you've got a value 0. And tree 3 makes a prediction that this client is going to claim. So let me ask you, you've got 3 trees, 2 of them say that this client is going to claim, 1 says it's not. So what would the final prediction be if you were taking a majority vote? Right? I think everyone would assume
1.
Yes, that's right. Final prediction will be 1. That's right. So we do that for each of these clients. We just follow the majority vote rule. And then this is the prediction that your final random forest model makes. All right, now, what I want to show you here is, let's look at each of these trees, right, individually. Let's look at tree 1, and I want you to ignore all the other trees on the right of it. Let's just look at tree 1. If we use only tree 1 prediction, right? So tree 1, if you look at the first prediction was 1, the second prediction is 1, third was 1, and the last 2 was zeros. Here's our actual outcomes. This is what the actual outcome is. All right. If you look at it, the actual outcome for illustrative purposes, let's assume everyone actually did make an insurance claim. All right. So everyone actually had a value of 1. Looking at just tree 1, you could see that it got the last 2 wrong. All right. So in other words, it got 3 right and it got 2 wrong. So it got 3 out of 5 correct, which is a 60% accuracy. Similarly, for tree 2, you got 3 right and 2 wrong. So that means it also got 60% accuracy. And tree 3 also did just as the other 2 trees. It got 3 right, 2 wrong. So it got 60%. So even though those 3 trees got a 60% accuracy, when you combine them and you look at the random forest model, now if you look at this model, here it got 1, 2, 3, 4 correct, and only 1 wrong. So it got 4 out of 5 correct. It's got an even higher accuracy. So by combining those 3 trees, even though their scores weren't that high, they were 60%. When you combine them, you can get an even higher score by combining those predictions. So that's what I want you to take away from this. All right, it's a very powerful and useful quality and characteristics of a random forest tree. So just like how I did this example here, I've actually left an exercise for you to do. I'll make the slide available for you. I'd like you to give this one a shot. Okay, so here are the predictions. So you just basically have to fill in the question marks. All right. I'd like you to give this a shot. I'll make this available after this session. And the solution is in the next page. All right, so I'm not gonna give you too much time to see it, but anyway, I want you to just give it a shot and compare the answer to the answer that's given. All right, so let me just come back to see if there's any questions. So far, so good. Hand raised, yes?
Yes, question. In slide 4, when I was
Slide
looking at
4.
your observations in the
Here,
trees, I saw some duplicates. Say in tree 2, you have exactly the same duplicates. Why would we have duplicates in the data?
because of this slide here. Good question. The sampling with replacement. Remember, you can have the same dot. Oh, sorry, wait, I'm not showing my screen. Yeah,
Okay,
because of slide 3. Because of
all right.
slide 3.
Okay, fine. Thank you.
No problem. Good question. Check the chat. Very, very good. Someone is ahead of me on that one. Okay, so you understand how different trees make up a random forest and how you get the final prediction. All right. I want to ask you a question, all right? And let me just get your intuition on this. Let's suppose I only had 2 trees. I only had 2 trees. That makes up my random forest. Now, if you had a majority vote, right? So you had this observation that comes in, right? Observation 1. Tree 1 predicts that this observation or client is a 1, right? This is what tree 1 predicts. Tree 2 predicts a 0, right? So you only got 2 trees. One votes 1 and one votes 0. But remember that trees, for classification and for all models, even logistic regression, all the models that you covered for classification, SVM, etc., you can get not only the class prediction, you can also get the probability that it predicts this value. So in other words, this tree 1 says it's 1 with a probability of 0.8, 80% chance. Tree 2 says this observation, the reason why it's making it a 0 is because its probability was way under 0.5. In other words, the probability of it being a 1 is quite low. It's 0.45. Well, let's leave it at 4. Now, because there's a tie here, and you only got 2 trees, what do you think? How do you think random forest would handle something like that? A draw, a tie? Intuitively, how would you do it? What do you think you would do? You've only got 2 trees. One says 1, the other one says 0, but you do have the probabilities.
Probably choose the one with the higher probability.
Not a bad. That's a good one. That is one way to do it. Yes. So the way you suggested is take the one with the high probability and make that the prediction. Very good. So that's one way random forest can do it. Excellent. Another way it can do it as well, just keep in mind, what it can do is it can average it. It'll add these 2 up and divide it by 2. And then the average will be, in this case, I think the average is 60%. Well, maths is right. So 0.6. So you could use the average, and this average 0.6 is greater than 0.5. So the final prediction would be a 1. That's another way to do it. Very good. So that's, just keep in mind that that's how random forest could treat situations where it's a draw. All right. Charity?
Evening all. Just a quick question. On the exercise that we are meant to do, right? I think
Yeah.
I'm a bit lost. I'm not sure if it's an error that has been made or if I'm the one that is completely out. I'm looking at the accuracy percentage, right? And it's not speaking to the observations that we have there. I'm not sure if maybe you can go back and share that example on the exercise and we look at the accuracy percentage. There we are. So
But
it
this
says
side,
there,
yeah.
on the exercise, it says there is 80, 80, and 40. But when I'm calculating the predictions at the top, it's not 4 out of 5. It's actually like 3 out of 5, and 3 out of 5, and 3 out of 5. So I'm not sure if maybe there's something that I'm missing here.
Okay, so let's look at tree 1, right? Let's look at the first row.
Mhm.
So it predicted a 1, right? It predicted a 1, and the true value is a 1 as well. So it's correct. Now, second value, it predicted a 0, and the actual value is also a 0. So it's correct. All right, let's see. Third prediction, it predicts a 1, and the actual value is also a 1. So it's correct. The fourth one, it's predicting a 0, but the actual value is a 1. So they're not the same. So it got this one wrong. And then the last one, it's a 1 and a 1. So it's correct. So it got 4 out of 5. Does that make
Oh, I
sense?
get it now. So we compare to the true outcomes, the true values that are
Yes.
on the right hand side. Oh, got it. I think I missed that part. Thank you so much.
No problem. No problem. All right. Yeah, so do give that exercise a shot. It's I hope you enjoy it. All right, so now I'm going to talk about something called OOP score. And I believe it stands for out of bounds score, right? So OOP score is a very nice quality that random forest has. All right. What it does is I'm pretty sure you're familiar with the train and the test data, right? The training data is what you would expose the model to. You would let that model get developed and you would train that model on that data. And then you would keep aside the test data, right? After you train this data, you would implement this model on the test data and see if it actually does well on unseen data. Now, what random forest has a good quality for is because you are doing sampling with replacement. Let's look at learner one, right? Learner one. When you're doing sampling with replacement, you can see that it didn't get this yellow point here. It didn't get that. So there are going to be colors that it didn't get. It also didn't get the red one. So what we do is you keep track of these points that these learners didn't get. So here, it's showing you that learner 1 and 3 didn't get the yellow dot. Learner 1, 2, and 3, all of them didn't get the red dot, right? Etc. etc. Learner 1 and 2 didn't get the green dot, and so on and so on. So what we do is we put these data points in a data set, all the ones that were unseen in at least one of the models, right? So this yellow one was unseen in one of them, the red one was unseen, the green, the brown, etc. So learner 1 didn't see the yellow dot. That's what we have in the first row. Learner 3 also didn't see the yellow dot. Now what we do is, because it hasn't seen that data, we will apply that data or make that learner make a prediction on the yellow point. So learner 1 made a prediction. And remember, this is all training data. So that means we know the outcomes. Okay, so we know the outcomes. We know the true value. So when these models make a prediction, we can tell whether it's correct or right, because we know what the true value is, and we just compare the prediction to it. So what happens is, for learner 1, when we applied it to the yellow dot, we found that it got a wrong prediction. That's why it's marked with an X here. Okay, it got the prediction wrong. Learner 3 also got the prediction wrong. Right? And remember, the yellow dot was only unseen by learner 1 and 3. Now let's do the same thing for the red dot. Now the red dot was not found in any of the models. If you look at these three of them, the red dot is not there. This is brown. The color isn't clear, I'm sorry. But this red dot is not in any of them. So that's why you will see them for all 3 models. So what we do is we apply learner 1 to the red dot. It got the prediction right. We apply learner 2 to the red dot. It got the prediction wrong. And learner 3, we got the prediction right. Okay, and we continue in this manner for the last 2. All right, now that we have that, we use majority vote. Okay, so look at this, the yellow point. Okay, look at the yellow point here. There's 2 learners, both of them got it wrong. So by majority vote, the majority vote will also be wrong. Okay, now let's look at the red dot. And let's look at the majority vote for the red dot. Learner 1 got it right, learner 2 got it wrong, and learner 3 got it right. So 2 out of the 3 got it right. So by majority vote, 2 out of 3 got it right. So that means the final one would be right. Okay, so we got a correct prediction here by majority vote. And so on and so on. Okay, for the green and the brown. So we got 3 out of 4 correct. Okay, we got 4 colors. We got 3 out of 4 of them correct. So your OOP score is 75%. So what you've essentially done is, the whole point of this is that you only had training data. We never touched our test data. We never touched it. Just by using the training data, we could make it into a test set, because not all learners were exposed to data points. And whenever that happens, we leverage that property. We make use of that. We apply it to the data point that it didn't see. So in other words, we create another test set that the model can use. And the OOP score is quite useful because you can improve the model performance by making use of the OOP score. All right. And it's a powerful tool, because all you've done is you only use training data and you've managed to use it to regularize the model to avoid it from overfitting just by using that one training set. All right, but I thought I would, yeah, let's share this property of random forest with you. Let me check if there's any questions on it. The arrow. Question, hand raised.
Yes, evening. Just
Hello.
referring to the previous exercise that you showed us. So what if with the two tests we have a probability of 0.8 and 0.2, where when you average it out, it's going to give you 0.5.
Good question.
What do you
All
then
right.
choose?
Yeah, good question. Now, I know for this example that I showed you where it's a draw, where is it? Sorry. Yeah, I kept the numbers very simple, 0.8 and 0.4. All right. But when you're actually doing this with data and you can't develop a model in Excel using, you can't develop a random forest model in Excel. You'd have to either use R or Python or SAS. When you develop this model, it is highly, highly unlikely you are going to get probabilities with this exact value. Often the model is going to give you values of 0.8, 1, 2, 3, 7. It will be to a number of decimals. The precision is it's high, okay? It won't be just at 0.8. And similarly for the 0.4, you're very highly unlikely going to get an exact 0.4, 0, 1, 2, etc. You're likely going to get something like that. So when you average them out, you wouldn't often get a value that's going to sit on the fence, all right? But let's say for your example, you had 0.8 and you had 0.2, hypothetically, right? So if we average them, you're going to get 0.5, right? So over 2, you get 0.5. Now, the way the default setting for random forests is, I believe it is a probability of greater than equal to 0.5, you make it a 1. And anything less than that, it becomes a 0. So with that being said, if you look at this value here, it's going to satisfy this. So even though it's 0.5, you'll have to make it a 1. Remember, 0.5 is the halfway mark, but it has to be set to 1 class. By default, the model uses this, but you as the user can change this. You can specify a different probability. You don't have to stick with this. And that's often done in practice, like for certain industries, like if you're working with, let's say you're trying to predict cancer, right? And if you predict a client, if a patient's that it has a high chance of having cancer, they probably have to go for surgical treatment. So you don't want to get that prediction wrong. You want that prediction when it says it's going to be a 1, that is that patient likely has cancer. When it does that prediction, you want it to be very certain. You don't want it to be like around 0.5. You can change that threshold to be 0.8. So the model says, okay, anything with a 0.8 probability and above, we will make it a 1. Otherwise, it's a 0. So you can change that threshold. Does that answer your question? Great, cool, good question. Yes, question.
Hi, yes. I wanted to ask, what is the purpose of the out of bound like calculation that we did?
The OOB, it's the whole idea here. I know the pronunciation. Okay, I wish I could find a better what do you call it, acronym, something for it. What it does is it allows the model to use training data as test data as well. There's a value of a model having test and train data, right? You never just have a train data for a model. You have train and test. Why do you have to train and test? Train is so that you allow the model to be fitted and developed and establish its rules. Establish rules to make the prediction. All right. Now, what do I mean by that? Well, last week you would have done decision trees. So remember, trees would have a set of rules. So it would say if a client has, if a client has an income of say less than 7,500 per month, and the client has debt expenses that are, let's say, 7,000 per month, then client is likely going to default on their payments, right? And the only way it could get those rules is by using the training data to get those rules, right? So you fit it on that. Now the test data is valuable because what you want to do is you want to see that this model that you developed is good at making predictions on unseen data. Okay, that's why you use this test data. So when you apply this model to the test data and the score is poor, so here on the training data, let's say the score is great, you had a 0.9%, 90% accuracy, right, score. But on the test set, it had a 0.4 score. So a very big difference, high variance. That means you overfitted the model. With the OOP score, what you could do is before you even applied it to the test score, you could use the model and use the OOP score to keep tweaking these rules so that the OOP score and the train score are very close. So the OOP score is probably 0.85. Right, and when you achieve this, so let's say this is the out of bounds score, right? When you achieve this, then when you apply to the test data, you could improve the result just by using that OOB data set. Does that answer your question?
Yes, thank you.
Welcome. Next, Nombuyo.
Hi. I just wanted to find out when we're looking at the table, like for example, the one where we had to do the exercise and stuff. So the final prediction, like what are we trying to show that like the random forest is better than individual trees?
No, for this exercise, it's to basically check whether you can combine the predictions to make the final prediction, and you can work out the final score. So you understand the
Okay.
methodology
Mhm,
behind
mhm,
how it combines it.
mhm.
Whether the score is higher or not, it's going to be left to you as an exercise to figure that out.
Oh, yeah. Okay, okay. So then the target outcome is from where? Like, did they just get it? Like,
Your target outcome is known. It's given to you.
okay,
The
okay.
true values, yeah, would always have to be given to you. The modeler never,
Mhm.
just creates them.
Oh, okay, okay.
Cool. JC?
Okay, thanks. My question is on the last part when we are doing the OOP score. If you can just go back there. I'm not quite getting. Okay, so we are saying learner one. Okay, when we are saying this, the unseen data, maybe when the learners were picking up, right? I want to understand. Are we saying learner one didn't pick the yellow one? Then we put an X, and then we're saying learner three didn't pick the yellow one, then we put an X,
No,
right? And then
no.
oh, how are we doing it? Yeah,
No,
maybe
no.
I'm lost on that
Okay.
part. Yeah.
Okay, so I see your confusion. Okay, all right. All right, so I'm guessing that you get that learner one didn't get the yellow dot. There's no yellow dot in learner one, and then there's no yellow dot in learner three. Okay, so these two learners didn't get the yellow dot if you look at their colors. So let's just focus on these first two columns, right? So we're saying the yellow dot was not seen by learner one and three. All right, so this yellow dot was not seen by learner one and three. All right, okay, so what we do is, let's just look at learner one. What we do is, to learner one, we apply it to the yellow dot. So let's say instead of, now forget the color of the dots, instead of the yellow dot, let's say the yellow dot is actually client number one. That's what the yellow dot is, it's the yellow dot. Now, we know what client number one's true out value is. We know what the true value is. Okay, because remember, this is the training data. So we know the true outcomes. Okay, let's say the true outcome was a 1, hypothetically. Now what happens is when you apply learner 1 to client 1, so let's just go back to a tree. When I say learner 1, let's just talk about tree number 1. Tree number 1 here. All right, tree number 1, which has these two variables here, age and mileage. What it does is it looks at client number 1, it looks at what their age is, looks at what their mileage is, and makes a prediction, right? And that prediction, if I go back here, is going to be a 0. Let's say hypothetically. There's a reason why I'm choosing a different value to what the true value is because in this last column, that's what the X is telling you. It's telling you that you got it wrong because the true value is a 1, but what it predicted is a 0, so it got it wrong. That's why it's an X there. Does that make sense?
I'm still struggling. Like when you then say client and then it just got lost. I don't know what we're trying to do by creating this. You said we can take it as another tree. That's why we score it. But then I'm just not getting how we get to it.
How do you get to the last column?
Like, how do you get to this last table that you have worked on?
This table here.
No, the one where you've got learner 1 and 3, and then learner 1, 2, 3, and the yellow and the 3 reds, 2 greens, 1 brown at the bottom. Like how you are coming up with this.
Okay. So maybe from this part here, you're not getting this part. Is that what you're saying? Start from here.
Everything else I was getting until we got to this OOP score and how we are then starting to assign these X's to each learner and how we get to the percentage, the 75%.
Okay.
I think that the yellow the figures there are the observations.
That's correct.
Right. So it's the X's at the end are just the prediction, the predicted outcome by your model, as opposed to what the true value was. So the X is when you get the opposite of what the true value is.
That is correct.
Oh, okay. All right. Yeah. So I think I'm all right.
Okay.
Thank you.
All right. Okay.
Thank you for that. All right. Okay. Okay. I'm glad that makes sense, but feel free to just stop me and ask me to explain anything you're not so certain about. All right. So that is random forests. All right. So now we are going to cover boosting. So let me just check. Susan, you have a question?
Hi, yes. May you please just go back to the slide of the OOPS score quickly so I can see if I actually also understand what was said.
Okay. Let me just clear out things here.
So from what I said just now, so this works the same way as the tables for tree 1, tree 2, and so on with the true outcome. So is that small table on the right the technically or true outcome? So then we use that to determine whether it's an X or a tick. Is that what's happening here?
Okay, the true outcome is not shown here. What is shown here is whether it got it right or wrong. That's what the X is. The X is telling you that it got the prediction wrong for the yellow dot. So what it could be, yeah, it doesn't make sense. Okay.
Yes, okay, I see it now. Thank you.
No problem. Okay, all right. Let's move to XGBoost, boosting, right? Now, there's a difference between boosting and random forests, okay? Random forest uses many trees, as does boosting, but how they use it is very different. So random forests, what it could do is it could train tree 1 on, say, one computer, right? So this can be trained on computer 1. On another computer, you could train tree 2, all right? And then in a third computer, you can train the third tree. So this is how random forest does it. Okay, so random forest does it like this. So in other words, those trees are trained independently of each other. You don't need them to communicate with each other. And then in the end, you can combine them to get the final prediction, like what we've been doing so far. That's how random forest works. However, boosting does not work like that. Boosting works by training tree 1 first, and then based on that result, you train tree 2. So you have to train tree 1 first, get the results, and then from those results, you feed it into the second tree. And then once you train tree 2 and you get the results, you feed those results into tree 3. So in other words, they are trained sequentially, okay, in sequence. So that's the biggest difference between boosting and random forests, okay? Trees are trained sequentially. Now, before we move on, it's very important that you understand how weights work and how they affect your chance of being sampled. All right. So let's look at this table here. All right. Weights basically increase your chance of being selected. So the higher your weight, the bigger your chance of being selected, right? In stats, that's how it works. But I'll explain visually how that actually makes sense. All right. So let's look at the first part, the first weight. We get a weight of 0.1. Okay. And then the second weight has a weight of 1. Let's just assume we have a highway, right? This is the highway that's that long. Now the first weight is 0.1. So it starts at 0. The first weight here is 0.1. Okay, so I'm drawing it pretty much to scale. The next weight is 1. So it's way out here. All right. Now, this distance is a lot smaller than the distance from here to here. So let's say this was the N3, right? The highway going from Joburg to Durban. If a plane was flying over this highway and it dropped something, right? Just entertain me for a second. If it drops something, does everyone agree that there's a much bigger chance of that object falling in this area here than this area here? So we'll call this area A and we'll call this length here B. Right? If you don't understand that, please let me know now, because this concept is very important, right? This is how weights work. Weights increase the interval. The higher your weight, the higher the interval. So if you look at the weight for the second row, that means it makes the interval a lot bigger. So if you had to pick something at random or drop something at random, there's a bigger chance of it landing in this interval here than this first interval. Okay, I've got no hands, but please just unmute and ask away, right? So that's how weights work. Weights pretty much create intervals, and the higher the weight, the bigger that interval. So when you pick a number at random, and Excel has a function called rand with these brackets here. If you have to just type that in, so I'll show it to you here. This is Excel. I'm just going to make it a bit larger so you can see it. Right. If you type equals rand, you see, it just gives you a random number like that. All right. So what it does, it selects a random number between 0 and 1. Okay. Now, This is important because the weights are used to randomly select these observations. So remember in the example with random forest, I used those colored dots, okay? And I showed you bootstrap sampling, where you can sample with replacement, all right? Now in that example, every dot had an equal chance of being selected. In other words, the weights were the same for all of them. But when you change the weights, then certain colored dots have a bigger chance of being selected. Or in other words, some clients would have a bigger chance of being selected than other clients if their weights were larger. And it's because of this principle of the interval being bigger for them. All right, check one more time. Okay, that's good. Okay, I got a question. Go for it.
If the interval, let's say there were like 5 weights, if the does the interval always go to the weight before? So like you have the 0.1, then the 1. If it's like 0.1, 0.5, then the 1. Would it be then between 0.5 and 1 and then between 0.1 and 0.5?
Yeah, so to your question, let me come back to the good question. All right, so let's say we had 3 weights. It was 0.1. This was 0. This could be 0. Let's say 3, and then the next one could be 0.2. Right, so they're not in order, right? But what that actually means is that if you have to create the, let me just remove this. Here's the total length, all right? So if we add all these up, you're going to get 0.4, 0.6. So it goes from 0 to 0.6, right? Because you add them all up, you get 0.6. So the first width will be 0.1. The second width is quite large because this one has a large number. So here it goes from 0.1 to 0.4. Sorry, 0.4. Why? Because the distance is from here to here is 0.3. That's the weight, right? And then this one will be, the length here will be 0.2 because that's the weight. Does that make sense?
Yes, thank you so much.
You're welcome. Good question. All right. Okay. All right. So now keep that in mind because we're going to use that principle going forward. All right. And I'll show you how weights come in. All right. So now I know this board is very busy. So just focus on what I'm telling you to focus on, right? So let's I'm just going to focus on this first table here. I want you to just focus on this table and forget everything else. And I'll take you through the whole process. So what we do is we have 5 clients. We're going to assume that we just start with 5 clients, client 1, 2, 3, 4, and 5. All right. The target class is what the actual outcome is, the true value. All right. That is the true value. So in other words, this client 1, the true value is a 1. Client 2, the true value is a 1. Client 3, the true value is a 0. So what we do is we start off with tree 1, and tree 1 makes a prediction on client number 1. The prediction is a 1. And if you look at the actual value, it's the same, so it got it right. Okay. Client number 2, it made a prediction on client number 2 and it got it wrong because the actual value is 1, but it predicted a 0. Client number 3 got it right. Client number 4 it got it right. Client number 5 it got it wrong. So it got 2 wrong. All right. So it got 2 wrong out of the 5, and I've also colored it in red to draw your attention to that. Now, when this algorithm starts, the weights of all these clients are the same. Everyone has an equal chance. I'm just going to check the chat for a second. Good. Okay. So when this algorithm starts, the weights are all the same. And if you look at the weights, they're all 0.2, 0.2, 0.2, etc. All right. So you can let's ignore this column for now, right? Because we're going to come back to that later. So just forget that. So the weights are the same for these clients. The first step, what we're going to do is we're going to look at those clients that it got wrong. And it's these 2 here. Got this one wrong, so the weight of that client is 0.2, and you got this one wrong, so that weight is also 0.2. So only look at the wrong predictions, which are those 2, and we add those weights up. Okay, so that's the total error. The total error is adding up the weights for the wrong prediction. So it's 0.2, 0.2, and you get a value of 0.4. All right, that's the total error. What we're going to do with this total error is you're going to feed it into this formula here, performance. This formula is called performance, and it's given by this equation here. All right, we feed this 0.4 into this equation, and we get a value for performance of 0.203. All right, now we are going to use this value, this performance, to update the data. Okay, so what we're going to do is we're going to adjust the weights for these clients by using this value here. Now the objective is we want the tree that's going to follow after this to focus on the predictions we got wrong previously. That's the what do you call it? The big advantage of boosting. The trees that get developed in each step only focuses a lot more on what the tree before it got wrong. So it gets better and better. If it got it right previously, there's not much need for the next tree to focus on the one that got it wrong, because it already got it. There's not much need for the tree in the next step to focus on the right predictions because it got it right. So what's the point? You want the tree to get better and better. So in other words, it needs to improve on the errors before. So what we do is we use this value to give a higher weight to the wrong predictions, and we want to give a lower weight to the predictions it got it right with. All right, so how we're going to do that is by using this formula here. So this formula, we use this formula here when you get the right predictions. So in other words, let's just look at client number 1, right? I'll just draw your attention to this client here, the first client. We got this prediction right. There's a tick here. Okay, we got this prediction right. So what we want to do is we're going to recalculate the weight for this client, right? And how we do that is we use this formula here. New weight equals old weight times E to the minus performance. And your performance value is 0.203. So what is the old weight? The old weight is what it had originally, which is 0.2. Okay, so let's just look at client ID number 1. Right, the old weight is here, 0.2 times E to the minus performance, which is this value here, 0.2003. And if you work this out, you'll get a value close to 0.16. Yeah, this value here. That's the new weight. Now, if you look at this new weight compared to what its original weight was, you can see the value decreased. It was 0.2, but now it's 0.6. So we decreased that weight because this formula here caused that. All right. Now, let's look at the second client, client ID number 2. Client ID number 2. Now, for that client, the prediction was wrong. Okay, you can see here, it's red. We predicted 0, but the actual value was 1. The target value was 1. All right. So because you got it wrong, we are going to use this formula. Okay, so when you have it wrong, you use this formula. The difference between these formulas, they look almost the same. But if you look at the exponent, this has a negative value. And this has a positive value. So this formula upweights it. So it increases the weight. This formula increases the weight. Whereas the one above it decreases the weight. Now for client number 2, we'll use this formula here. So the old weight, client number 2 is 0.2 here, times E to the positive performance. So it's positive 0.203. And if you work that out, you'll get a value of 0.25. Now look at the weight for client number 2 in the second iteration. Okay, it's higher than what it was before. It starts off with 0.2, but now it's 0.25. So it's got a higher weight now. Let me check the chat. Everyone following? that. So the incorrect predictions, we increase the E. E is in your calculator. If you got a, I'm assuming everyone got a Casio calculator, but if you don't, on Excel, E is the exponent function. So let's say you want E to the 0.203, right? So you'll type E equals to EXP 0.203, like that. It's a function in Excel, for instance. Okay. Why does the weight increase? All right, Susan, good question. There's a reason why the weight increases, right? Now, let's go back to one slide. One slide. Remember what we said here. We said the bigger the weight, the bigger your chance of being selected. All right? The smaller the weight, the smaller your chance of being predicted. So why are we increasing the weight for the incorrect predictions? And it's because we want to give them a bigger chance of being selected again. Why? Because we want the predictions that were wrong to get picked again so that tree number 2 can focus on the incorrect predictions and improve the model. That's how the model gets better. If the model only focuses on the correct predictions, it's never really going to get better. You need to get it better at fixing its mistakes, in other words. So that's why we want to choose the wrong predictions again and again until this model gets better, until the final tree, let's say tree number 100, can iron out those mistakes. Does that make sense? Cool. All right. So we follow these formulas for each of these observations and we get the new weights, right? We get the new weights here. In the next column, all I'm doing here is I'm normalizing the weights. So what does normalizing mean? All it means is I'm going to add up all these values. Okay, so if I add them all up, I add all these weight values, I'll get a total of, the value is, a second, 0.98. All right, so I add it all up, I get 0.98. Right, I add this column, I get 0.8. And then for the value for client ID number 1, all that value is I take the weight that it has, 0.16, 0.16, and I divide it by this 0.98. If I do that, I get 0.17. That's the normalized weight. For client number 2, how I get this 0.25 is simply just taking 0.25 for its original weight, 0.25, divided by the same total, 0.98, and I get this value here, 0.25. Normalizing just means making sure that they add up to 1 now, because now when you add this column up, you'll get a value of 100%. That's what normalizing does. That's all it does. It just rescales the values so that when you add them up, they will equate to 100%. All right. Now, from that slide before, remember what we said, right? The bigger the weight, the bigger your chance of being selected. And if you look at client number 5, so let me just use a different color here. And I'll maybe use red. Let's look at this client here, client number 2 and client number 5. Remember, we got them wrong. Okay, we got them wrong. So you can see their weights are a lot higher than everyone else's. And that's what you want because those predictions were wrong. So we need to give them a higher weight. And then all you do after that is you create a cumulative column. Let me just change the color back. These two columns are just essentially what we were talking about in the slide before, where we create these intervals here. These intervals here, so we can make selections in these intervals. So in other words, let's just focus on this first column here, cumulative column. Cumulative column is you just keep adding up these values in the column before going down. Okay, this column here, you add the values going down. So 0.17 is the first value. Then if you add 0.17 to 0.25, you're going to get 0.42. And you add the next value, so on and so on, until the last value is equal to 100%. Right? That's the cumulative column. All it means is you're adding up all the values down the column before going down. Right, now once you get the cumulative column, you can create the ranges or the intervals for each of them. So remember, this first value here, the interval is from 0 to 0.17. Right, the next value, the interval goes from 0.17 to 0.42, etc., etc. So that's why these two intervals are the largest. The second one and the fifth one, because those predictions were wrong. So because the intervals are the largest, they'll have a better chance of being selected again. Let's go to the chat. Any questions so far? Please let me know if there's a question, okay? Now, how do we use intervals to make the selection? Well, remember I told you that rand function in Excel, okay, that rand function selects a number between 0 and 1. So if you just keep selecting numbers at random between 0 and 1, so let's say, hypothetically, I ran the rand function, okay, and I selected a random number of 0.32. Okay, I got a value of 0.32. Looking at all, sorry, I know the board is a bit busy, I'm just going to clear it. All right, say I picked a random number, 0.32. Okay, that's a random number I picked, 0.32. Looking at these intervals, where does the 0.32 fall? Which client would be selected based on the range on those intervals? Remember, the value I picked is 0.32. Okay, does that 0.32 lie in this interval here, the first one, or does it lie in the second one?
In the second one.
Very good, excellent. So because of that, client number 2 is going to be selected. That's how you use the random numbers. The random numbers, if they fall in any of those intervals, whichever interval they fall in, that's the client that gets picked. So next, if I draw another random number, 0.81, that's going to be client number 5, etc., etc. Now you can see, because client number 2 had such a big interval width, that client ended up getting picked 3 times. And that's what you want, because you got that client wrong. And that's how you do the reselection. So now client tree number 2 is going to be trained on these client, and the process just starts all over again. That's it. That is the process. It's just one tree making predictions, right? Then checking which predictions are wrong. Based on those wrong predictions, we resample. And then these new samples are going to be the data set that the next tree is going to be developed on. And the process continues for however many trees you have. If you have 100 trees, this process continues sequentially 100 times. Everyone follows that? Cool. All right, everyone, thanks for sticking with me. We're at the last step now. The last step is actually the interesting part, in that how do we make the final prediction now? You have all these trees that have been trained, okay? How do we make the final prediction? The final prediction, it's very, very similar to how a random forest works, okay? Now, random forests use a majority vote, okay? So let's say tree number 1, you have tree number 2, and tree number 3, all right? If tree number 1 predicts, let's say this is a prediction. If tree number 1 picks a 1, tree number 2 picks a 0, tree number 3 picks 1, then the final prediction is going to be a 1. Right? That's based on a majority vote. Now, boosting does it slightly differently. All right. What it does is it gives more, it allows more say for trees that have a better performance. All right. So in other words, think of it this way. If one tree is very good at predicting, it's going to have a higher weighting in its vote. Okay. And that should be the case, especially for this algorithm, because as trees progress, they get better and better. So you want the trees that are doing very well to have a bigger say in the vote. So we take that weighting into account. And how we take that weighting into account is by using this formula here. That's what it does. All right, so I'll talk you through this with an example. All right, let me erase this. All right, so you've got learner 1, right? Let's say learner 1, hypothetically, it got a 90% accuracy. So it got it right 9 out of 10 times. So the accuracy was 90%. So in other words, its error was 10%. 10% or 0.1. So that's tree number 1. It got an error of 0.1. All right, 0.1. So if you take this 0.1, that's the error, and you plug it into this equation, because that's what this E represents here. This E is actually the error. Okay, it's the same thing here. It's not the same E in the calculator, it's your error. If you plug the 0.1 into this formula, you'll get an alpha value of 1.1. Now what that alpha is, it's how much weighting you give to tree number 1. Now, because if you look at tree number 1, it got the lowest error from all of them. Because it got the lowest error, it should have the most say. So that's why when you do the same thing for each of these trees, learner number 2 and learner number 3, you'll see that its alpha is the highest. So in other words, the weighting given to its vote is going to be higher than the other 2 trees. Good. Okay. All right. Finally, what we do with those alphas is we take the average using those alphas in the average. Okay, there's just one twist that we do when we're doing this prediction. Okay, normally I told you the target or the predicted value would either take a 1 or a 0. Okay, but when you're doing this average, instead of making it a 0, we make it a -1. Okay, the reason why we do that is because the math doesn't work out when you make it a 0. In other words, if you use 0, those weightings will mean nothing. They just disappear because 0 multiplied by them is just going to be 0. What we want is we want the sign of the prediction. So when we work out this average, if the sign is going to be negative, then we'll make it a 0. That's the prediction. If the sign is positive, then we'll make it a 1. That will be the prediction. So it's just in the math, in the calculation, that instead of 0, we use -1 instead. So what we do is, the formula is, let's say tree 1, right? Hypothetically, tree 1 predicts y equals 0, all right? But remember what we said, instead of 0, we're going to use -1 instead, right? So tree number 1 made a prediction of -1. Let's say tree number 2 predicts a 1 for the target value. And tree number 3 also predicts a 1. Right? So two out of the 3 trees, these 2 predicted a 1. But the 1 tree, which is learner 1, predicted a 0. If this was random forest, the final prediction would have been a 1 because 2 of them voted as a 1. Right? If it was random forest, but it's not random forest. We are going to use the weighted sum. The weighted sum is basically, let's just look at tree 1, right? I'm just going to focus on learner number 1. Right? Remember what we said? It predicted a 0. Learner 1 predicted a 0. In other words, we are going to use -1 instead of 0. So what we do is we take its alpha for learner number 1, which is alpha 1, this value here. and we multiply it by its prediction. So it's going to be alpha 1, which is 1.1 times its prediction, which is -1. Okay, because remember, instead of 0, we're going to use -1 instead. All right, so that's learner number 1. We do the same thing for learner number 2. Learner number 2, it's going to have its own alpha and its own prediction. All right, so its own alpha is 0.2. That's its alpha here. So it's 0.2 times, and its prediction is given here, which is a 1. It's 1, which is just 0.2. All right, and you do that for learner number 3. Same process. It's going to be alpha 3 times its prediction. So that's what I'm doing here. This is tree number 1, this is tree number 2, and this is tree number 3. And then you add them all up. You take the weighted sum, you add them up, and you get a value of -0.7. So what do you think the prediction is? Remember what I said? The 0 is a -1, and the 1 remains as a +1. If it's a negative prediction, the target class is predicted as 0. Otherwise, it's 1. So you've got a negative value. So that means the final prediction is it a 0 or a 1?
0.
Yep, that's right. And that's the difference here. If this was a random forest, the prediction would have been a 1 because of the majority vote. But with boosting, because that first tree is strong, it gets a lot more say. So it actually pulled the vote for the final result to actually a 0, a target class of 0. All right, that is it. That is it for boosting. The floor is yours. Any questions? Anything that wasn't clear, please do let me know. Okay, so takeaways from boosting. Boosting is also made of a number of trees, but they train sequentially. All right, so the first tree will start off with an equal weighting for everything. The next tree, let's go back here, improves on the tree before it, but it only focuses on what the tree before got wrong. So whatever it got wrong, those get a bigger weighting. And those get pushed into tree number 2 to train on. And hopefully tree number 2 improves on that. So now it may get it right. All right, so it's very unlikely it's going to get pushed to tree number 3. But whatever this tree gets wrong, it's going to get pushed to tree number 3. There's a bigger chance of it being pushed to tree number 3. And then finally, in the end, we take a weighted average as the final prediction. Cool, that is it for me this evening. Any questions? No one? Was it clear? Okay, I'm hoping it was. That's why there's no questions. Andrew?
Sorry, I have a question.
Go for it.
Yeah, in terms of application, what would you use, like random forest for, like getting like a general idea or like a baseline, and then if you wanted like accurate results, then you would use boosting?
No, that's a good question.
That's the main difference between the two in terms of.
Good question. Very good question. So random forest is actually a competitor to boosting. The most popular boosting model is XGBoost. It's very widely used, but often random forest competes with XGBoost. What I would recommend as a baseline model, if you were only looking at tree-based models, look at decision trees. Make that your base model. Just to look at one decision tree, right? Try the decision tree and the data. And then you implement random forest and you implement XGBoost, and you compare those results to the decision tree, the single decision tree. If it doesn't beat the decision tree, you'd rather take the decision tree because it's simpler. it's easier to understand. It's only one tree and you can understand that flow diagram that explains the rules. When you start using XGBoost and random forest, it's very difficult to interpret the result, even though it's better performing. Often it's better performing than a single decision tree. And you lose that interpretation, right? So if the decision tree performs the same as the random forest and the XGBoost, rather use the decision tree. But very often, if the random forest performs better than the decision tree, then obviously you should take the random forest. And then you would compare random forest versus XGBoost. Whichever one of those two performs better, that's the one you would likely take. Does that make sense?
I think so, yeah.
Yeah, so remember, a decision tree is very easy to interpret. As you saw last week, you get that flow diagram, right? Let me see if I can destroy it here. It'll tell you salary greater than something, 7,500. If it's a yes, go this way. If it's a no, go this way. And then here, another decision, and it predicts a 1. So let's say a client comes to you. Oh, so I'm sorry, I wasn't sharing my screen. All right, so here, let's say age was another variable. 25. All right, so it does these splits and you can easily understand the reasoning behind the decision tree. All right, so to explain this prediction, it's easy because you can look at this diagram and explain it. And this is the decision tree. So you would, I don't know why these are coming up. Okay, so if the decision tree performs the same as a random forest, if it has the same performance, rather go with the decision tree because you can understand the prediction if the performance is the same. If, however, the random forest performs better, you'd rather go with the random forest, but you lose that interpretation. Random forest isn't always chosen over or boosting and vice versa. You have to test both of them and check which one gives you the better result. So it's never certain which one is going to perform better until you actually apply both of them. Oh. Any other questions? Was this clear to you? Is anything that you weren't sure about? Okay, I'm taking the silence as everyone's good. Okay, but even if you do have questions, please reach out to me. You have my email. I'll make this presentation available to you and the recording as well. And yeah, thank you for joining and great questions, everyone. It was a good session. Have a good evening.
Thank you. Bye.
Bye.